Okay, welcome everybody. So I'm here with Tracy, who has joined today's session, and we're gonna go a little bit over the mathematics of the principles of linear regression. And we will then focus on the lab solution. So for the simple lab assignment that was given for the last lab, which of course, again, I forgot to change the date. My apologies for that. It's due on, no, it's actually due on June. So actually peak, where am I in June? It is due on, June, today we have the 1st, 2nd, 5th. It's due on June 5th. Okay. So please forgive me if I have a little oversets like that. I'm still trying to catch up on things. After the long weekend, I'll get better with these things. Hello, there's somebody else joining. Welcome. Hi, how are you?
Hello.
Gregory, hi.
How are you?
Nice to meet you in person.
Nice to meet you.
So I just started. So the session is being recorded, just for you to know and be aware. So Tracy, who also joined, asked for a little bit of a recap of linear regression, and we can briefly go through some of the materials, and then let's focus on the lab solution. So I'm saying all of this under the assumption that you have had a chance to watch the recordings, go through the intro slides, and go a little bit through the code. I'm not going to sugarcoat it. 2 months for this course is quite intense, so it will require quite a lot of work from all of us, essentially, not just from you, also from me, also from us together. And I really want to be very close to the pulse of your learning curve here. Particularly R can be very challenging. And I have programmed R for the last 12 years. I do have a fair amount of experience with it, so most error warnings I should be able to help you. And if you don't mind, Craig, that you would go on mute if you don't speak.
Oh, sorry.
That's okay. Yeah, so I should be able to deal with most of your concerns in terms of programming and coding the labs. As for the theory, we can go through the theory. If you have questions, let's please also connect to our discussion board, and let's save also these check-in sessions. I will try to keep these review sessions as frequent as possible. So I was told that Mondays and Wednesdays is most suitable to your schedule by Professor Kelvin. So I will gravitate towards scheduling these for Mondays and Wednesdays, because I think there's an epic class on Tuesdays. We meet on Tuesdays and Thursdays. So I will do my other best to do Mondays and Wednesdays. The only caveat, I will be traveling in Europe for 2 weeks. Tracy raises the finger, great, thank you. I will be traveling in Europe, so I will need to push them a little bit early in the day, which I am not sure is quite optimal for most of you. I hope that still you will be able to join. We could do something like a lunch session, like lunch with me, and we could try to approach it that way. Otherwise, it would be recorded. So I will record the sessions, and we could communicate via discussion board. Or alternatively, there's always the possibility of a one-on-one. I happily always make myself available and try to schedule something as a one-on-one. And we can go over things individually if there are really problems that occur beyond those that can be handled via discussion board. So again, so we are mainly focusing on linear regression, and we will be coding the examples in R. And so I hope the understanding is still quite well when it comes to linear regression from PubH 614. I have taught PubH 614 now in the spring semester, so I do know what you have learned. I'm trying to kind of translate it into how we're approaching things now, because now the focus is really on regression, and that was essentially handled in 2 classes in published 640. So we remember that we have a mean, we have central tendency, we have markers of central tendencies, we have means and medians, we have variability around these means and medians and these central tendencies, which are classified here by the so-called standard error of the mean. So again, you are essentially assuming that in a sample, you have a random variable. This random variable is a sample of a larger population. And you mean to essentially estimate the variability of potential sample means that you may have drawing from the same population. So essentially the way you're doing is you have a random variable, and you conceptually, you're drawing little subsamples, and you create means for each of these subsamples, a random infinite number of subsamples, and you get this large number of means, and they all also have a variability around this true mean of means, which is supposedly identical to the population mean. And so now essentially this variability is here shown with the standard error of the mean. So this is the variability of these sample means around the true mean. And when you calculate confidence intervals, you have these confidence intervals that are meaning to capture with a 95% confidence the true population mean within their bounds, within a set score of 1.96, within which you capture 95% of your population. You mean to extrapolate it to your population, right? So this is how you estimate the confidence intervals. So this being said, essentially that calculation here, we're meant to start off, is essentially nothing else by 1 to n, where n is essentially the number of these samples, and yi indicates the number, and n is the number of sample size, whereas yi is the number of samples drawn. And then essentially the standard error of your y bar, which is essentially your mean, is essentially then distributing around this y bar, around this actual mean. So now we can construct around this a t-statistics for a one-sample t-test. So in a one-sample t-test, you're comparing your mean against a true population mean or any reference value of interest, right? So you have a mean plus you have a variability. And you have this normally distributed, which is one of the major assumptions of a t-distribution, where you have a t-distribution from a sample which resembles a true normal population distribution. And you have with yi, you have your repeated samples. So this being said, if you are now assuming this to be the residual error of your estimated yi, your y, you have a variability that distributes around an n of 0, which is your mean, with a variability, a variance that is essentially depicting the standard error of the mean. So if you would employ this now for a 2-sample t-test, where you have a yi at an x equals 0, where basically 0 and 1, this x becomes the definition of the groups. So this is your nominal variable in a way transformed into a binary variable. So you have 2 groups that you're comparing. You have male versus female, or you have, I don't know, hypertensive versus non-hypertensive. You have 2 groups. You're transforming this into x equals 0, x equals 1. You have, again, the n. This becomes your mu. This is your population mean or your sample mean, with a variability around that is a variance, a sigma squared, whereas yi for x equals 1, which is the second group, you're essentially looking again at n with a mu, a sample mu, plus a beta, which is essentially the difference between those two samples, but again distributed as a variance squared. So in a two-sample t-test, you calculate the difference of these sample means. So essentially that difference, so the idea of a two-sample t-test is really that you take a sample from, you take a subsample from one sample and you take another subsample from the other group, from the other sample. You take this out, you build the difference, you keep the difference, you draw the rest of that subsample back into your original sample, and you get your first difference. And you do this infinitely, in an infinitely amount of times, and you basically get this distribution of differences, of sample differences. And these differences you essentially testing against your null hypothesis is that they are not different. So you're testing this against the zero. So this in an arithmetic way, in a mathematical format here, essentially, you have a difference for y bar where x equals 1 minus the difference of y bar where x equals 0 will allow you to estimate your beta. And this is the beta from here, where you basically have mu plus the beta. And if you rewrite this, you essentially come to this format where your yi equals the mu plus a beta xi, which essentially is that x, which is either 0 or 1. And the way this is coded here with a 0 and either a 0 or a 1, this difference only becomes mathematically operative if x equals 1. So that's how this arithmetically as an amount finds its way into the estimation of the yi. And again, this residual error is again normally distributed around 0 with a variance. And so this is essentially the recap of a t-test, and this is where the t-test finds its way into a regression model, where you have two groups. So just as a recap again, you have the same relationship. You have this beta being the difference that gets operative when xi equals 1. And then you basically add this up and you come to that difference between the two groups. And you can estimate your y in the presence or absence of this mathematically operative beta xi. And so if you rewrite this in that format, you basically get here to a beta 1 that essentially allows you here to express this mathematically. And this is where you basically add your regression model, which is, and this is important as a take-home message as well. So a linear regression is an additive model, meaning it's additive in a way that you estimate an actual value. So your yi is an actual value on the y-axis predicted by whatever you see on the x-axis. So this is an additive model as opposed to a multiplicative model, which is a logistic regression, which we will do later in class. So this multiplicative model allows you then essentially to estimate the intercept and the slope, where the intercept is essentially that y value where x equals 0. So that's on an x equals 0. So this is where your regression function crosses your ordinate, crosses your y-axis at 0. The beta 1 is essentially the increase with each increment of an x, whatever that x is. So we will, so if we have x as a continuous variable, it's the increase of a y with increase of 1 unit of the variable on the x-axis. So this is essentially the interpretation of a regression function as shown here. And this is where it intersects with the t-test, because if you hypothetically, if this is not a continuous variable, but it is a dichotomized variable, it's a binary variable, then it only becomes mathematically operative if this becomes 1. And that's how this basically adds up then to the estimate of your yi. I hope this kind of illustrates a little bit the underlying mathematics of linear regression as far as we came now with the first two classes. And when it comes to birth weight, we have essentially a special situation So was this clear? Let's take a minute. Was this clear to some extent as an explanation how the arithmetics of linear regression present at this point in time? Tracy, particularly you asked the question whether this could be briefly touched on.
I'm sorry, can you repeat the question?
Does this to some extent help with the question that you asked about the mathematics of linear regression per se?
Yes. I wrote in the chat that this was very helpful. Thank you.
All right, I'm happy to hear that. Okay, great. Okay, so this was basically the transition from a t-test to linear regression and a brief discussion of the linear regression as a mathematical function. So now when coming back to the actual class, and now we're jumping on to class 2, because essentially this was then brought into practice. And now we're going to simple linear regression using continuous data. So mathematically, again, we have the same concept. So we're estimating a yi. We're relating yi to a beta 0, which is our intercept, plus a beta 1, which is our slope, multiplied by an xi, which in most cases is now a continuous variable. In the special case of a binary variable, where the intercept with the t-test comes in again, this would be a binary variable, either plus or 1. But the principle is the same. It always indicates a numerical increase by 1 unit on the x-axis. This is basically the underlying principle of that. So now when you want to relate this in a more simple format, you have dependent variables, systolic blood pressure, you have an intercept A, you have a slope B, and you have your independent variable serum glucose, labeled here as SL, and you have a residual error, which we ignore for now. It's normally distributed around 0 with a variance in a normally distributed function. Then we have this essentially is the corresponding R code, which we're going to get to later. And that essentially will allow us for hypothesis testing, whether there are associations and whether we can estimate our dependent variable. So in essence, what you always need to kind of visualize in front of your head whenever you're confronted with linear regression, you have a dependent variable on your y-axis, you have an independent variable on your x-axis, and this 1 unit increase is literally an increase that corresponds with a slope, a line that is fitted through the scatter. And this, in the simplest format we have done, was a Pearson correlation, which is essentially nothing else but quantifying that association between two variables without much detailed information about it other than the associations, where we're basically testing it against a flat line, where basically our yi is nothing else but the mean of yi. So if we go no further, we can also extend our estimate by basically adding additional covariate. So now we will talk about different models later on, and about the definition of confounders and how to predict variables accounting for confounders. And you know from epidemiology, you know enough about DAGs and how careful you need to select confounders when you include them in models. So this will also be part of this class later on. So you're treating now all these predictors in a way that you are allowed to build a y hat. So this y hat is basically your predicted y, and with your residual error, you can quantify the accuracy of your prediction. This allows you to test the model and test the accuracy of the prediction. Good. Expected. Then you also have some special cases where for that association between systolic blood pressure and serum glucose, there was the example of the centralized regression. When you centralize your independent variable, you centralize it towards the mean. So essentially now you're not testing these increases of 1 from 0, but you're centralizing and you're measuring basically your increases from a mean, which will affect your slope estimate. So this allows you to basically avoid the situation that you have an biologically infeasible kind of starting point with the intercept, where a serum glucose of 0 is not compatible with life. So for that very reason, you are basically taking as a reference point your mean glucose level. Okay, so this would have been the theory that I thought just briefly to discuss for you. Are there any questions on this? No? Okay, so I see shaking heads. So let's quickly go into the R portion of. Did you all have a chance to look in the RMD code? What's your background, Gregory, for example? What's your background with R? Are you?
No background whatsoever.
No background in R. Okay, good. So I hope I was able in the lab to outline quite detailed what R is all about. I think the intro slides are quite well and explaining quite well what R essentially is. Just as a brief recap, you're looking at RStudio. So RStudio, were there any problems to install any of the softwares, any problems with the RMD, with the Markdown exporting?
I have the R in the studio. What is the Markdown? How do I install that?
Yeah. So you have Markdown, essentially it's already installed, and there's a difference between R and R Markdown. So this is a simple R code. It's nothing else but a text file, right? And Markdown file, an RMD file, is in its nature a little bit different. It allows for a mixture between text in a certain way that can be exported and can then essentially be presented in a PDF or in an HTML. And within this text, so this is text coded in a way like LaTeX would code it. So LaTeX is kind of a coding language that allows for you to code written words. So you can write whole papers in LaTeX. It's a little bit of a learning curve to get a handle on it. I personally don't use it. I'm still an Office user, but you can basically use LaTeX to code words in the outline that you see here in the white part, and then you have for Markdown you have these so-called Markdown chunks. So these chunks essentially allow for you to implement R code chunks into your text, and this will present. So this is essentially the lecture that I just showed you, which Professor Sang coded for his. So this is essentially the class of Professor Sang, which I think I mentioned in the lab. So he coded all the material, and so essentially you will here see. Find this first. Wait. So this is essentially exactly this part of the Markdown. If you go in the Markdown, it will display it in that way. So if you start with a hashtag before the actual heading, it will present the actual heading in this fashion. And you can specify the fonts, you can specify the sizes, so you can manipulate along a lot with this particular coding. So what you then have, you have R Markdown. You indicate that you want to implement such a chunk with 3 apostrophes in the beginning, 3 apostrophes in the end. In a curly bracket with R, you define that this is an R chunk. And everything in this chunk is essentially then our code. So this is a little bit of a learning curve and will require a little bit to get comfortable with, but it's going to be fine down the road, because the basis of everything is really R. And no matter whether it's in a markdown or it's not, R follows simple principles. So you have here an R script in front of you, and that's the one that we did in the lab. So you have here clear definitions where you can define objects. So R is an object-oriented, line-oriented programming language. That means you need to have objects defined that end up here in your so-called environment. And these objects essentially will then be handled by your script, will be ran in your console here on the lower left quadrant, and will create outputs either with Markdown as a PDF or as plots, for example, here on the right lower quadrant. So this being said, you can define your objects on various ways. The simplest way is to just say X equals, so this is the equal sign in R. This is a smaller sign and the hyphen that is essentially then followed on the right-hand side with whatever you want to pack into your object. So if you do X equals C 4 to 6, you get an X equals 4 to 6. So with C concatenate, you're creating a so-called vector of 3 numbers. If you do the same now with Y, you get the same corresponding vector for Y. So now you can do various things. So now you have X defined, you have Y defined. Now you can measure the length of Y. And this is a very powerful function, because hypothetically, if you have a longer vector, or you take a variable from a data frame as your vector, you essentially can use this input from length to calculate proportions, right? If I say, for example, length of X divided by length of X, where X is greater than 3, and this is how I can specify it. I essentially get here a proportion. So I get here 3 divided by, actually would be the other way around. So that's not a proportion of it. So I could make it in this format. So that's how I get a proportion of those entries that are greater than 3 out of all entries in X. So this is the way you can use all these information that you get out using this function. So there's the length function, there's the sum function. You can let's bring it back in the original format. So you can manipulate your analysis, and manipulate is not the right word, but you can instrumentalize these functions to basically serve your analysis. So with sum, you get a sum of your X. So if you, for example, if you have a binary variable and you have entry of 1,000 people that are, and you code binary, you say, okay, so out of 1,000 people, 500 are male, 500 are female, and you code this as male equals 1 or female equals 1, you basically, with the sum function, you can get the sum of all ones. And by that, essentially, you know how many individuals are male or female in your data frame, in your variable, in your binary variable. And you can utilize then something like sum divided by length to essentially get the proportion of entries that are male or female. So this is how you instrumentalize these functions. And this is, it's different than SAS that categorizes a priori and basically takes all these entries and treats them as factors, and then approaches them with in a more function-oriented style. This is more a programmatic approach, where you essentially programmatically utilize the functions to get an output, and that output you're going to be working with. So you need to think a little bit more stepwise. You will likely, once you get a little bit of a start on it, you will get a hang of it. It's a little intimidating in the beginning, and I know I've autodidactically learned R like 14 years ago, and it can be a little bit frustrating in the beginning, but It's an extremely powerful tool. I'm a very passionate R programmer, and you will surely enjoy it. So you can do various things. So you can build a sum of x, you can build a sum of x squared, which is essentially nothing else. And this is to be kept in mind. So there's just like all arithmetic operation, it follows the same mathematical rules than any other operation or any other calculation. So if you do a sum of x squared, you're squaring them first, then summing them up. If you do sum x and then square, then you're essentially squaring the sum, right? So it's arithmetically important to pay attention to these details. So then we have x plus y. So with x plus y, essentially what happens is it sums up each individual entry. It's very iterative, meaning it will not calculate automatically the sum of all numbers together. It will sum the first entry of x with the first entry of y. It will the second and then the third. So this is also if you know it, it can be a blessing because you can again utilize it. You can utilize it, and we will utilize it later. So x multiplied by y, same thing. You get again 3 entries for each row of x and y. You get again the same arithmetic operation. X minus 2, same story. You can do 7 to 11. The column basically gives you a sequence. It tells you that there will be a sequence that you're following along that basically is here from 7 to 11. So it's 7, 8, 9, and it fills the blanks for you, which is also a very useful tool, because if you have let's say you have an x of x equals 1 to 11. 11. Let's not do x, let's do x1. You have an x1 from 1 to 11. That's now 11 entries, which are 1 to 11. And you just want to have x1 from 4 to 6. You can also get it out in that format. So you can selectively extract with the column over longer chunks of your data. Then there's the sequence function. I think I also talked about it in the lab. So you can build sequences where you basically go from 2 to 9, just in the same format with the column, or you do it by 2 increment steps. You do it as 4, 6, 8, 10. Comes to the same end. You can also do this in a format that is going backwards, essentially. So you can do this in various shapes and form. You can iteratively repeat entries. You can repeat them in various functions. You can repeat sequences, and you repeat only those sequences. So with the, everything after the comma will give you the number of repeats. Also keep in mind, if you want to learn something about a function, you can also use a question mark, and the function will basically get you to a help menu where you can study in more detail what you want to do. What's really important, it's line by line by line by line. The end product of every code is that you essentially press Command A and you just run your entire code, and it does all the analysis for you. And the beauty of R is really that this can always be done. And this essentially, it's a standalone code that will do exactly what it has done yesterday in the way you have saved it. You can also call different codes. You can call codes that you have saved somewhere as a script. It will load it into your current setting, into your current code, and it will run that code for you. So you can develop functions down the road. You load these functions and you save these functions somewhere in a separate folder. Whenever you need one specific function, you just call that function from that folder. This is what I utilize quite often, essentially, for my work. It's quite useful. So, so we can, for example, we have now here a little vector. We do x2, it takes the second one. Everything that is following your object in a bracket will specify what you want from that object. So x2 is the second entry in your vector. But all of these exercises, you will do these exercises quite extensively in DataCamp. And I hope you all have received the invite and you have had a chance to get familiar with it already. And yeah, great. No, it's just DataCamp. So it is just an absolutely wonderful learning platform, and I highly recommend it. It will really give you a strong step forward, and you will definitely enjoy working with it. Okay, we have L. What else we got here? Yeah, so you can build summaries of all your subsets. You can do various things. You can build matrices, which is also quite nice. This particular the matrices, you can then you can build 2x2 tables using matrices. You can, for example, you can with row names, you can individualize. So you can do males and females, for example, for row names. This will allow you to basically I don't know, I'm doing this in the console. No. Oh, no, that was not. So we're building a matrix. If we do now row names of X would be C, male, and female. Gets you essentially now to a 2x2 table. So you can now, for example, you can do call names. With call names, you can define your call names, and you can say, let's see, HTN or no, HTN. HTN is an abbreviation for hypertension. So you can hypothetically, you can build a 2x2 table that you then can use. Let's say with a chi-squared. So there's a chi-squared function, and you can do this quite easily. So then you just need to do chi-squared of X, and you have your chi-squared there with all your analyses. Yeah. Okay, but this was negative. This is not gonna go. Okay, so this would be a chi-squared of this virtual table, right? So you can see you can do a lot of really cool things very fast and very efficient. And this is really what the beauty of R is. It's very efficient. Once you have the code set up, you can manipulate and you can change fractions of that code. Very simple, and you can run just the things that you want to update. And then with Markdown, essentially you can then also very swiftly get this in the format that you export and share, for example, with professors or with your boss or whomever you're creating a file for. So please go through all these questions. So you have, I don't want to go too deep into these things now because we have limited time. You can, okay, maybe this is, okay, data quakes. So you also have always data examples available. So this is an earthquake data set where you basically you have earthquake data, which is internally in R, part of the packages. And you can use this data to train models to just evaluate functions, try to understand functions. Usually each package that you will load comes with some form of a data package that will allow for you to employ these functions. So all the functions that are part of the package are essentially then referring to data sets that are contained in the package. It's very useful. And you will see for all the labs, you will see the MT cars quite a bit, which is a very classical data set to employ functions. So we have talked about the summary aspect. So summary, so everything in R is basically an object. So even if you have a summary function like this, even the summary function here is an object. So you can pack the summary function here in an object, And from that point on, your summary A is that summary of that particular variable. So you can then you can with ls, I didn't mention this one, ls means list. So ls gives you basically an overview of the environment. So in our studio, you have it graphically depicted here in the right upper quadrant. In base R, you didn't have this right upper quadrant. So you basically, this was the way how you could assess your environment. And you can see how your environment looks like and what it contains. So if you test now, this is true for the environment, but this is also true for objects. So if you want to know what A contains, you go on, okay, no, it doesn't do that. Okay, take it back. I thought it would do it. But basically what you can do in A, so if you want a specific value from A, which is our summary extracted, it doesn't give you a list, so that was my misthinking, but you can get a specific entry from A. So let's say you want a summary, you want the first quartile, you can get it by summary depth, or A2, you can get summary depth. You can get this summary command. And if you do 2, you basically get the same. So you can utilize again the summary function to get individual values out that you can then use for reporting or further calculations. So with the apply function, you can get means of certain subsets. So subset is another, so we get to that later. So you have, with quakes, you can basically apply a certain function of a certain data set to a certain subset that you're interested in. This is the computing simulation. So you can always simulate data. You can with dnorm, pnorm, qnorm, you can create simulated data that will follow certain distribution functions, and you can essentially get also the calculation out of, so pnorm will give you a p-value for a certain normal distribution, right? So if you go 2 standard deviations, this is coincidence. Okay, so it's not this, but you can characterize a normal distribution using pnorm, where you essentially standardize your mean and your standard deviations, and by that you can utilize pnorm to build you a normal distribution, and you can utilize this to quantify your standard deviations and your proportions of the population. Okay. Yeah. So this would be a mean around 0. This is the Q1. So this is 84% of the population, for example. So this is how you would be able to standardize your population and find out what the set score table actually would give you in access to that, right? Okay, but now let's go further here. So we have X is R norm of 100. So basically X becomes now a normal distribution from 1 to 100. And you can now get with X, you can get a normal distribution, and lengths are norm plot. So this is simulated data following certain outlines that you have at your disposition. You can then fit functions through, and you can always use the plot function to illustrate this data in any shape or form. So this would be temperatures, so again, this is one of these internal data sets. So these are temperatures over the last, from 1910 to 1970. Okay, so these are essentially those additional data functions in addition to what has been discussed in the lab. And when we look now at the lab solution, so we have here a lab assignment. So the lab assignment essentially asks now for the import of a SAS data set named French males. And we want to know the dimensions of these data sets. We want to write the name of the variable. And then we want to save it as mydat.txt using a write table command. We want to save this, then read it, and then create some summary statistics, develop a dependent variable and age as your covariate with a simple linear regression model, provide a fitted model, provide the interpretation of the estimated model parameters in above question for y-intercept and slope. So now the first thing you need to do is, and you remember how I talked earlier about you want to characterize what's in your data set. So this is LS. So this gives you all the objects that are in your data set. If you want to remove everything from your environment, you basically use the so-called RM function. So if you write RM A, it will remove A. If you want to remove a list of objects, which is consistent with LS, which is all the objects in your environment, you basically have here the code. That is here the starting code that clears your entire variable, your entire objects in your environment. So you have RM list equals LS. This cleans your entire environment from any object. You then need for loading a SAS file into your environment. You need, unfortunately, you need external packages for that. So SAS follows a certain data format that is only read by SAS, and you need help to essentially transform this into something that R can deal with. So there are two libraries that have that are a suitable tool to essentially do that. So one is SAS7bdat. So this is a library, this is a package that needs to be installed. And so now we're coming to installing our first package. So installing a package is done with packages. You come to the repository, you have the packages to be written here. You go on SAS7bdat. Now you just click on install, and it will install to a repository that R has created. Important is that you select install all the dependencies, because the dependencies are these packages that are needed by that particular package. So I have this package installed already, so I'm not going to go ahead. The second package that we will need, and I'm just going through that. The second package that actually allows you to read SAS files is the Haven package, library Haven. That is another package that allows for the reading of SAS files. One problem that will be quite a constant, or let's put it that way, it's something that you will always need to be aware of, that you need to understand where is my data. And I don't know whether you're on a Mac or Windows. Tracy indicated she was on a Mac. I'm
on a Mac too. Yeah, yes. Mac.
Okay, great. Because Mac is actually quite supportive. So I don't know which OS you're at, but usually you can quite simply, if you make a right click on it or you press Control and you open up your Finder, you go on that file, you click Control, you open up this menu, and you press now Option. It will change the layout of this menu. So you have here you have where the copy line changes to copy French males.dat as a path name. And that's beautiful, because if you click on that, essentially it will give you exactly that path name. including the file name. And this is super useful. This makes life very, very easy. So there are in the lab, there's also file choose. So file.choose. Was it file.choose? No, yeah. I don't use it really, so I don't know. It's actually parentheses. I don't use file choose really. Yeah. So file choose allows you to actually get this opened up. I recommend against using it, to be honest, because it kind of makes things a little messy and complicated, and it interrupts your flow. So you can press Command A and just run the entire code. So it interrupts the flow. I personally will always recommend to set it up at one point. I also would not do it this way, personally, but there are different ways, like with set working directory, and this is how Marcel and Bino set it up. And it's a very convenient way to do that. So I understand why they did it, and it makes a lot of sense to do that. Another way is to basically define a path name and a file name. So if you do path name, you basically take this, you take the path, you put in parentheses, and then you put it in brackets. And now this path name is exactly your path, right? And if you do now file name is this French mails. So now you have path name and file name. And if you want to reattach it, you can do this with the so-called paste function, and you do paste path name and file name, and you can basically put it back together. And that's neat, because if you do paste sep equals separator equals empty parentheses, so that takes the space out. You get it now without the space, and now you can use this to use the read.sas7bdat with exactly this. And now you can automatically pack it into your file. So this is the elegant way. In my head, it's a very elegant way, but it requires a little bit of patience to set it up in the first time. But it makes it interesting then later on when you write files, because I usually, the way I would set it up, I would put it together as a read path name and a write path name. So then I have automatically separated the data files that I'm reading and the output files that I'm writing. By that, I'm a little OCD about my organization. So it makes it a little bit easier, because down the road, if you end up with like 10 different data sets, and you have temporary data sets, and you have then in the end, you have reports that you're printing out, it just makes it easier to organize it that way. But again, this is up to you. I'm not, I think at this early stage, it's important that you have a functional, workable, operational way that you're comfortable with. So I think this is just for down the road, I recommend to approach it that way. So, but now we have this data file loaded. We have here year, age, death rate, and log DR, and log of the death rate. And so now we can work forward with this. So we can now rename, so we don't need that. So also, because I'm seeing it here as an equal sign rather than the smaller sign and the hyphen, they're following the same principle. They mean the same. I personally, as a base R user, I prefer that I was quote unquote raised in a way that I would use the smaller sign and the hyphen. I do not know of a downside using an equal sign instead, except for that it's frowned upon by the passionate R users. So I would recommend to still stick with that, because there may be a downside which I'm not aware of, or that doesn't cross my mind right now. But yeah, I would probably go with that rather than the equal sign. But hypothetically, you can use the equal sign too in most cases, I think. So with class, you basically, so now what we need to do, because we loaded it in as an df, now we need to resolve this. So now we have my dot, we have this loaded now. With class, you essentially, you investigate already. What do I have at hand? So my dot is a data frame. So again, you have data frames is just another object. You have model outputs, you can linear regression models, you can pack into objects. So this becomes a different object type. You have vectors. So if you have, oh no, we don't have to. So if you have a vector, for example, 1, 2, 3, 4, 5, and you do class X, it will basically tell you it's a numeric vector. That's all it is. So class basically gives you an overview of what is that object actually. With dim, you get the dimensions. Always general principle, first the row, then the column. So it gives you the number of rows and it gives you the number of columns in your data frame. You can, with write dot table, you can essentially now write your MyDat file, and you can do this with your path name. So you can actually use now the paste path name file name. No, cannot do that. We need to my.txt. Okay. my.txt. So now we have written that. And now if we go into our Finder, we essentially see now my.txt as a text file. We can now, on the next step, do you have a question?
Oh no, I have to run. I have to get the kids to bed. Sorry.
Okay.
Thank you.
Okay.
I'm gonna do some work tonight after they go to bed and see where I get.
Sounds good. Please utilize the discussion board if you have any questions. If you run into questions, I'm running through the rest of these lines, and I will give some explanations if you want to watch the recording.
Okay. Thank you.
Okay, you're welcome. Have a good night. So, so now it's me alone. So I'm basically continuing on this. You're writing with write dot table. You write this file into that folder that you have defined. You can now with read dot table, you can read this file again into your environment. So you can now with remove, you remove everything, and with read, you can read it. Now with my data, you can do a summary. A summary gives you an overview of that age. And with summary, my data log dr gives you an overview of these log of the death rates. With hist, you get a histogram of your death rates. And with plot, you basically show now the relationship between my data age and my data log dr. So you basically, you get here, you always get, when you plot, you get as the first entry, R will treat the first entry as your X and the second entry as your Y. And this is basically how it's depicted here. So you have a Y of the log death rates, and you have on the X, you have my data age. You can now, with, so we want now a simple linear regression between log death rate and age. This is between log death rate, log dr, and age. We're basically using the LM function. that you know already from the code, from the RMD code, from the Markdown code. So you're building a linear regression model. You build a summary of that linear regression model. And with the summary, you get here a lot of information that R provides you. So it gives you the residuals. You remember the residuals are basically the inaccuracies in the prediction. So it basically gives you the y minus y hat. So the yi minus the y hat I. And it gives you these differences between the actual observed point and the predicted point. So this essentially distributes in a normal distribution around a mean of 0 in a normal distribution. You remember from the lecture, right? So this is essentially our residuals will here, and this residual error distributes around a mean of 0 with a variance of sigma square. And you can essentially see that here. So this is it's not a beautiful normal distribution because the mean and the median in a perfect normal distribution would both be 0. So there are some deviations, there's some skewness, and the skewness can be observed also then in the markers of the first quartile and the third quartile, where you see that in magnitude, they're not symmetrically distributed, right? Which is also what we see here in the plot, where there is a little bit of a band, essentially. So if there is a linear function fitted through, which we can quickly do, so this would then app line, my fit would give us an idea to what extent the estimates are deviating, to what extent the observations are deviating from the predicted. So you see that this is now the perfectly normal distribution, and there's some skewness to this data. So it's not massive, but it is there. So with summary, you get all this information. You get here with the coefficients, you get here estimates, which are intercept and our slope. So this is the beta 0, this is the beta 1. We get a standard error of these estimates. We get a t-value of this distribution. Again, this t-value is then defined by the residuals and the p-value corresponding to the t-value. Now we will talk about this all in much detail. So we have a residual standard error, which essentially is this standard error of all the residuals on 277 degrees of freedom. We know that we have 279 observations, but keep in mind, degrees of freedom is always the overall sample size minus 1 for each variable. So now we have 2 variables and we have 279 observations. So it's minus 2 variables gets us to 277. Then we have a multiple R squared being the proportionate reduction in error, which means this is the error that is being explained by the model. This is the proportion of the error that is explained for by the model as a proportion of the overall error. So the overall error is essentially all the noise and error that this data makes from the mean of y. So an adjusted R square is essentially again the proportionate reduction of error, but adjusted for the number of variables included, which arithmetically always has to be smaller than the unadjusted R squared, because you're penalizing for the number of variables that are being included. So if it's only 1, it's only obviously not penalized as much, but will then become more with more variables. With an F statistic, you basically have here an F, and remember from ANOVA, and this is where the linear regression overlaps with ANOVA as well, because you essentially get an F statistics where the between groups variability in the ANOVA is divided by the within groups variability. So you're basically relating the variability within your variables to the variability between the variables. So you basically have 3,410 on 1 and 277 degrees of freedom. So this is the between groups variability, and this is the within groups variability. And this F statistic, given that it likely exceeds this critical value, is at a p-value that is smaller than 5%. So it's a significant model estimate, so to say, over the model, significant. So we have then basically, here we have the plot the fitted line. We can now, my data age, log the, okay, so this is this plot with lines my age and y hat. Oh, I left this one out. So my hat, with the predict function, you can basically predict your estimate. So you get, if you are now predicting, you get 279 predicted estimates. And these predicted estimates are essentially what you will be plotting next. And as you can see, this is essentially a predicted line. So this predicted line, essentially, if we were to look at this, this is the same as ebb line. But the prediction essentially allows for prediction of each individual point. So we have essentially with the predict function, we can, if we had predicted age, we could use the predict function to essentially use our model to predict individual values based on our data set of interest. Okay, so this is the lab solution. This is essentially the lab for class 2. Please make sure to complete this within times. So it's due on June 5th, then it will receive the full 2 points. Make sure to put it in a markdown document, please. That would be nice. Again, markdown documents can be opened, can be built by opening a new file, clicking on R Markdown. So you go here on R. Here you can either create a new script, you can create a new Markdown document. You select what format you want to create it in. And then you have lab 2 assignment. You basically add your name to the assignment, my name, and then you can populate the markdown in the format that you fill out and respond to all these questions. So I hope this was somewhat helpful. I will be awaiting your question on the discussion board, and please make sure to do the data camp assignments. Make sure to really get comfortable in R and make sure to study the material. And we will be in touch next week. The next 2 lectures will be posted by Monday morning, and you can continue with the next classes. All right, so have a nice evening and hope to see you next week.